Hello, and welcome to our periodic law unit. Today we're going to introduce the periodic table, talk a little bit about the history of how the periodic table came into development as we know it today. By about the mid-1800s, there were about 60 elements that had been discovered. As this was continuing to grow, so some common examples of some early discovered elements are listed on the board. Some of the solids that were discovered were some of the non-reactive metals that we also think about as very valuable, useful metals like gold and silver, copper and iron. We also see bromine and mercury were two interesting examples that are found at room temperature. And some common gases like hydrogen, oxygen, nitrogen have been separated as well. As the number of elements grew, we kind of needed a way to group them on a chart because people sometimes needed to be able to look them up and find out things about them, kind of like we do all the time. So scientists wanted to arrange elements on the periodic table based on their properties. There were a lot of chemists who looked at this, a lot of scientists in general who looked at this. The one who's kind of most famous for actually creating the precursor to our modern periodic table is the Russian chemist Dmitry Mendeleev. He published a periodic table in 1869. It is argued that some other scientists produced something pretty similar around the same time, but he does actually get the credit for this. His periodic table and many of the other early periodic tables were based on two things: mass or atomic weight of elements. So the masses, just like we use today, were actually one of the ways that these were put in order. And also something called combining capacity. So combining capacity is really a way to discuss bonding ratio. So I'll talk about that in just a second. So if we look at this early version of Mendeleev's table, what you're going to see for elements is like lithium equals 7, for example. If you look at the periodic table, lithium's atomic weight listed on the periodic table is pretty darn close to 7. He has hydrogen listed as 1. That's pretty similar as well. So a lot of elements they were able to determine atomic weights for, so he had that information. He grouped them this way, these columns up here, by their bonding ratio with oxygen. So for example, how many lithiums would bond with 1 oxygen, or how many magnesiums would bond with 1 oxygen. And that's actually kind of related to the way that elements are grouped today. So combining capacity really means bonding ratio, which we actually have already talked a little bit about. So if you look, for example, at potassium or sodium, and you bond it with chlorine. So because potassium has a +1 charge, and chlorine has a -1 charge, they bond in a 1-to-1 ratio. If you compare magnesium to that, magnesium's charge is +2. So when it bonds with chlorine, it bonds in a 1-to-2 ratio. So he didn't use chlorine, he used oxygen bonding ratios instead. But what he found is because magnesium bonds in that ratio of MgCl2, so a 1-to-2 ratio, he actually looked at calcium, and that has the same one. So magnesium and calcium go in the same group. Sodium, as we know, bonds to chlorine with a 1-to-1 ratio. So they bond at the same ratio, they go in the same group. Mendeleev's table was arranged by mass primarily. Around 1914, this actually was changed. What Mendeleev did that's actually really great, if we go back to this table for a minute, is he left some spaces in here. So some of these places you see dashes were actually places that he predicted elements to be found. Right here, actually, the one that he has equals 44. Equals 68, that's actually gallium. If you look at a modern periodic table, zinc is next to gallium and below boron. So he actually made some great predictions of elements that had not been discovered yet that he thought would be discovered, such as gallium, scandium, and germanium. In 1914, Henry Moseley comes along, and he modifies periodic law. So our current periodic table isn't truly arranged by mass. Now, very often, the masses of the elements increase as you go up the periodic table, but the actual thing that dictates where elements are is really their atomic number, not their atomic mass. So he said that the properties of the elements are based on atomic number. The modern periodic table is therefore arranged by increasing atomic number. Creators of the early periodic tables couldn't explain why some elements acted similarly versus other ones. Now remember, in the 1800s, we were just coming to know what actually protons and electrons were. We had really no understanding of neutrons. So keep in mind, parts of the atom, we've got nucleons, so we got protons and neutrons, and we have electrons. So we were actually pretty new into understanding the parts of an atom, so it made a lot of sense to use mass in the beginning. But then we came to find out more and more that the number of protons is actually what identifies how an atom is going to behave. So once we kind of had more of an understanding of protons dictating that behavior, and electrons having to do with bonding and all that kind of stuff, it then made a lot more sense to make sure that our periodic table is arranged by atomic number, and that is not the same as older models, which were based on mass. So the current modern periodic table is not arranged by mass. That is extremely important to understand. Periodic tables are useful to chemists because it organizes elements according to their properties. The kinds of predictions that we could make could either be physical properties, or chemical properties. So sometimes it can be a little bit confusing, like, oh, should I be, grouping things by up and down columns? Should I be looking at left to right rows? So what kind of helps me remember how the periodic table is set up is looking at it like you would look at a calendar, okay? So if you look at a calendar, most of us have, pretty similar feelings about certain days of the week. If I asked you what your favorite day of the week was, I doubt you would say Monday. So most people are like, oh, gross, all Mondays are so bad. A lot of people love Friday because you get the whole weekend ahead of you. If you have a part-time job, you may not be as stoked about the weekend as some other people. But in general, the types of activities that you do on a particular day have a lot to do with the day of the week that is. If you're in an activity like karate, you might have karate every Wednesday, for example. So generally, all Saturdays are pretty similar. Just for example, as we look through the week at the different things that we do on different days, we see a lot of differences. Monday is a lot different from Thursday, is a lot different from Friday. So we see a lot of changes as we go from left to right. So this is kind of similar like the periodic table. Whenever we look at an up and down group, we're going to have very similar properties. So magnesium and calcium and strontium actually bond and behave pretty similarly. They're all solids and STP. They have a lot in common like that. If we look on the other hand, across a row, we see a lot of variation there. We have metals, we have highly reactive metals, we have non-reactive transition metals. We get over the other side of the periodic table, we have things that are found as a liquid at room temperature, we have a noble gas. So we have a lot of variety in properties as we go from left to right. When elements are arranged according to their atomic number, their properties are periodic or predictable. So when we go across a row like row 4, for example, so if we're looking at row 4 across here, the beginning of row 4 started with potassium. When we end up back down at rubidium, we're going to see a repetition of properties. Rubidium is going to have some similarity in its behavior to potassium. Elements that are in the same up and down column, remember columns are like the columns in a building, they are vertical, not horizontal, are going to behave similarly. So to kind of wrap this up, we call this modern periodic law. When elements are arranged by increasing atomic number, there's a periodic repetition of their physical and chemical properties. Reminder, our periodic table is arranged by increasing atomic number, not mass. I know I'm saying that a lot. It's important. So because of this repetition, in arrangement, the overall periodic table is based on atomic number. Our groups are vertical columns. Those are going up and down. Our periods are horizontal, and those are labeled on your periodic table. You can see where it says groups and periods. And those are going horizontal left to right. So groups, everything in the same group is going to have the same number of valence electrons. Sometimes that gets a little weird in the middle of the periodic table, but that's especially true in our representative groups on the edges of the periodic table. Because they have the same number of valence electrons, they're going to have a great deal of similarity in chemical properties. There's often a great deal of similarity in physical properties as well. This will tell you oxidation state or charge, and will predict how something will bond. So anything in the same group is likely to bond in a similar fashion. Periods are arranged by increasing number of protons or increasing nuclear charge as you go across them. Everything in a period has the same number of PELs. Everyone in the fourth PEL or in the fourth period has 4 PELs, for example. This will really just tell you the number of PELs. There's a great deal of variety as you go across the periodic table, although it does give you some insight into the size of a particular atom.